While vacuum tubes are required for high power and higher frequency microwave work, they are costly, large, and power inefficient devices that are difficult to manufacture. Solid-state electron devices, on the other hand, are small, lightweight, power efficient, and much less costly than tubes, making them ideal for use within low-power microwave circuits. There is thus considerable development activity in solid-state microwave devices, which is advancing this technology to increasing frequency and power levels. There is another major distinction between vacuum tubes and solid-state devices that is important to understand. Tubes have all of their operating and resonance circuitry within their structures. They are usually completely self-contained. Solid-state devices, however, are designed to operate within circuits with external components that determine their operation and resonance. Like the small chip components, the solid-state devices are also chips, or they are packaged for insertion into standard strip-line circuitry. In this sense, the solid-state devices are more versatile, as each mass-produced device can be used over a wide range of frequencies and to perform a variety of functions. Vacuum tubes, however, are usually single-function devices with their operating frequencies predetermined by their design. When microwave transistors are placed into circuits, there are many factors that must be considered in obtaining optimum performance from these devices. Adjustments must usually be made after the devices are connected to other components in the circuits in order that they operate at specific frequencies and power levels. The simplest case may only require the adjustment of bias current or voltage with a trimmer resistor, or the adjustment of frequency with a trimmer capacitor or by tuning a coil. In the most complex of circumstances, the actual strip-line circuit paths may require trimming with a tool or even a laser beam. Solid-state microwave devices can be divided into two categories: two-terminal devices such as diodes, and three-terminal devices. Microwave transistors are three-terminal electron devices that operate on the principle of signal transfer. That is, they transfer signals from their inputs to their outputs, amplifying signal power in the process. Also, like vacuum tubes, these amplifier devices can be made to oscillate and generate signals by feeding back a portion of their outputs to their inputs. When used for microwave applications, transistors generally fall into two categories: bipolar devices and field effect devices, called FETs or FETs. Bipolars and FETs are distinguished by the materials used in their fabrication and by the way in which they amplify signals. Bipolar transistors are generally made of silicon, while the microwave FETs are usually made of gallium arsenide. With bipolars, the input signal current controls a higher output current to achieve amplification. With FETs, the input signal voltage controls the device's output signal current to achieve amplification. In circuit applications, the distinctions between bipolar and field effect microwave transistors can be generalized by their power and frequency ratings. The silicon structure of bipolar transistors typically allows for higher power operation than comparable gallium arsenide FETs, but gallium arsenide has much greater electron mobility than silicon, so the FETs can operate at higher microwave frequencies than bipolars. Both transistor types are designed using techniques which increase frequency response primarily by reducing the thickness of the device's elements. When the transistor's elements are thin, however, the device's power handling capacity is reduced, so there is a trade-off compromise between frequency and power in the devices. Even with special fabrication, however, the ultimate high-frequency response for silicon bipolar transistors is still limited, usually to less than 10 gigahertz, because the electrons cannot move at higher rates within the silicon material. Often more significant than frequency response is a microwave device's noise figure. Noise is the random frequency signals generated within electron devices that mask the low-level signals they may be required to amplify. The lower this noise level, the more sensitive the amplifier. Gallium arsenide FETs have much lower intrinsic noise than bipolar transistors and are thus ideal as amplifiers of microwave communications signals received at antennas. Bipolar and field effect transistors have become the predominant electron device for amplifying low-power microwave signals at frequencies below 12 GHz. Research and development of new techniques for improving the performance of these devices will assure their increased use in this field.